Okay, welcome back. We have now another nearly 1 hour to discuss the third chapter, which is rather short, and then continue with velocimetry. So first of all, I would like to discuss a bit more detailed the requirements for diagnostics, and here especially comment a bit about the high temporal resolution we can achieve and the at least reasonable spatial resolution, very often not sufficient to resolve all scales. So for that we have to consider that our lasers emit coherent radiation. And this radiation typically is well focusable, such that you can create spot sizes and thereby small spot sizes and probe volumes that are well, relatively small. But the size is, as I said, it's relative to what you want to resolve. So the best you can end up with is a laser in terms of the beam profile with a TM00 mode. And that is, for those who are not familiar with this kind of expressions, that is the transversal electromagnetic mode. And 00 means that it's a Gaussian distribution. So let me draw that Gaussian distribution, this TM00 mode, into this approaching laser that comes here from the left. Then you would have a profile of the intensity over this spatial domain, which is looking like a Gaussian. For that case, you have now, due to the fact that you have here with the lens and with the finite dimension of the length, something like an aperture, and you might remember, I guess from school physics, that you then create here an interference pattern, an area pattern, where you can calculate for the main maximum, the zero order, the diameter, and this diameter is actually dependent on the focal length. It is dependent on the wavelength and the diameter of the laser beam at your lens. And typically the wavelength is given. You have a certain laser selected for your purpose, such that this is not easy to vary. What you can more easily vary is the focal length of your last lens, that is here assuming that you have parallel light approaching from the left. And there, of course, your limitation is more from your process. Because you have a hot flame, very often an enclosure, you might not be able to get as close as you wish. That's why a working distance very often is limited in the order of 200 to 400 millimeters. Let's take here for the example 350 millimeters. So here as well, as you see directly from this relation, the shorter the focal length, the smaller the spot size. And that's why very often you try to get as close to the process as possible. Then the remaining quantity is that you can expand your beam at the lens. It might come out over your laser with only 2 or 3 millimeters, maybe like a dye laser. And then it's good to have a telescope to expand it, maybe to 10, 20 millimeters or something like that, because that makes as well a huge impact. And something like 10 millimeters is easy to achieve. Using now, for the example here, 532 nanometers, then you get a spot size diameter here in the order of, let's say, 50 microns, which is an ideal case, because very often your laser does not, especially if you have pulse lasers, it does not behave as well as you wish. You not only have the Gaussian mode. So in reality, just a second, in reality, very often using these parameters, 350 millimeters, 532 nanometers laser radiation diameter, let's say 10, 12 millimeters or so, you end up with something like 200, 300 microns. Okay.
You may have said this already, but what's special about a wavelength of 532 nanometers?
Okay, that is selected because these are cheap photons. These are cheap because you have a crystal that is nowadays in a control way to create, that is neodymium in YAG, and that emits at 1064 nanometers. And then you have frequency harmonic generation. We call this 2 omega generation, where you half the wavelength or double the frequency. And you just have, after the YAG laser, a crystal where you have, for a given temperature, select the right angle, and then you can create, with the efficiency of more than 50%, 532 nanometers. And that is, with a very reliable system, relatively cheap. And you can even go further. You can double the doubled, for example, and go to 266 nanometers. It's a price concern, reliability, and these laser systems work if you treat them properly. They can work for decades. I have a laser system in my lab working for 30 years without any problem.
So theoretically, if you wanted to take operando measurements on the laminar diffusion plane using synchrotron radiation, which can give you like submicron resolution, would that be plausible?
First of all, we don't have a cyclotron. And it might be difficult to convince people to put an engine close to the cyclotron. Don't know, maybe that happens. However, if you want to go further in the UV, you end up in problems below. It already starts at 200, let's say 40 nanometers, because then you have hot oxygen and that absorbs. If you go below 200 nanometers, you will not transmit anything into the region where you have where you plan your measurements. And so that is a natural limitation.
There's actually some interesting work being done with X-ray imaging. I mean, they specifically do it, I think, for droplets, but yeah, they're trying to.
Yes. It's a line of sight method looking through the spray and looking for voids and things like that. Yeah, it is, but there is at least a debate about the interpretation. Okay. You get some, of course, information, no doubt about that, but it's maybe not all you would like to learn about is a very dense spray close to the nozzle. X-ray is used for that purpose, yes, as a line of sight method. Yes?
If I'm taking a laser profile at my focal plane, trying to experimentally verify this R value, should I be using half width, half maximum, or?
Yeah, what I do is 1 over E squared. Where the 1 over E would be 36%, and 1 over E squared is even smaller, and that is what I take as, let's say, the beginning and the end of that profile. And the best is to take a beam profiler. You take the laser as it is, you operate, and maybe you have a combination between a polarizer and a wave plate, half wave plate, and thereby you crank down the energy to prevent that you directly shoot or destroy your beam profiler, but then put the beam profiler directly at the focal plane is maybe the best. All right, let's have a look now how to compare these scales with scales in turbulent flows. An important quantity is the so-called integral length scale. And those of you have been courses in fluid mechanics, I guess, know it, maybe not all of you. What you need for that is you have to integrate about the so-called spatial covariance. And that spatial covariance is a normalized value of the averaged product of the velocity fluctuation at a certain location x of, let's say, the axial velocity component and, for example, the radial or as well the axial component, so you can have all mixtures, but measured at a location which is displaced by the distance r. They are taken at the same time. So if you take this normalized covariance in space and integrate it over this displacement r, you get then this integral length scale, and you can see that as an average size of a turbulent eddy in your flow. And these integral length scales are typically dependent on the geometry of your system. We have had early on this morning this turbulence generating plate with holes in the order of 4 millimeters in this opposed jet. And so those holes would control this integral length scale. Make them smaller, the integral length scale is getting smaller. Make them larger, they get larger. What can you do about it? You can use this information to estimate, assuming homogeneous isotropic turbulence. It might not be true, but that's the best what you can do. You can use the turbulent kinetic energy that is simply calculated from the velocity fluctuations to estimate the so-called dissipation rate. You throw that without any derivation here. You use that in combination with the viscosity and using that relation, and you have an estimate of the so-called Kolmogorov scales. And that is the smallest eddies before they dissipate into heat. And those eddies are now under the assumption of the homogeneous isotropic turbulence estimated. And here, using the premixed flame that we have discussed earlier this morning. And ideally, you would have a full resolution if your spot diameter is smaller than the smallest eddies. And here, for the non-reacting swirling flow, you see here at a certain location, x is the axial direction, r is the radial direction. You see here this spatial covariance. 1, 1 means that is composed out of 1, 1 axial velocity components to build up this spatial covariance. And then this is in x direction, where you have then the second location starting from that initial location. Your second probe volume is now shifted stepwise, such that you have in different directions here different spatial covariances, as well different in different locations, the flow field, or you do this in radial direction. So you measure still the axial component, but your second probe volume is not shifted in axial, but in radial direction, plus minus, and you end up as well with different correlations. However, the integration below, if you now take an integral, for example, from this here, you would take this area, and typically people take then the first zero crossing. Here it would be more difficult. You might have to extrapolate that. It's not really accurate anymore. But based on that, you end up with something which is in the millimeter scale. So typically for these flows, at these Reynolds numbers, we have here something 5 to 10 millimeters. Rather large if you compare it to the spot size, which was 50 microns. So there's no problem to resolve the integral length scales. However, if you compare it now with the Kolmogorov length scales, calculated based on the integral length scales, you end up that they're in the similar magnitude. Already, a flow with only Reynolds 10,000, you're at the limit of resolution. If you go for something under pressure, if you go for gas turbine conditions, you have no chance to resolve it optically. And the reason is you cannot do it like in biology. You cannot place your lens as close to the region of interest as it would be needed. So in practice, often you do not fully resolve it. And thereby, as I mentioned earlier as well, you end up with filtered quantities, independent of what you measure, velocimetry or scalar measurements. You end up with filtered quantities, and there is not yet an agreed best practice how to compare experimentally filtered values with CFD filtered values. And those of you doing, for example, large eddy simulation, you do have a different kind of filtering. You're filtering your conservation equations, and because of the nonlinearities, it depends on the stage where you do the filtering. A similar way of filtering would be a fully resolved DNS. You resolve everything in the simulation and then apply the filter that you have from experiments. Then you would receive the same quantities. But actually here, very often people do not characterize in their experiments the experimental filter size. And I don't say it's difficult, and you have to have it's only estimated, and it's an effort. And so for these practical reasons, still there is no best practice. Okay. In time, everything is much easier. Because of the way these lasers work, I have mentioned this Neodym-Yak laser, they as well have a certain way to pulse them that is called a quality switch, where you build up the inversion, and then by a trigger you release you enhance the quality of your optical resonator, and then you have a huge pulse coming out which eats up your inversion within a very short time. So these are the short pulses in the order of nanoseconds. And then, by the way, because of these pulse radiations, you can increase intensity dramatically, and that's why later on we will talk as well about nonlinear techniques that are building on high intensities, which become feasible only by pulse radiation. However, coming back to the main route, you can now as well define an integral time scale, not a length, but a time scale. And here you have to integrate over the temporal autocovariance. So if you look to this definition, it looks quite similar. For example, you can take here the axial and the axial, or axial and radial in radial direction, whatever you want. Typically, you're mostly interested in axial and axial. And then you measure at the same location, the same x location, but you shift the second measurement not in space, but in time. And using a normalization, you can end up with a Kolmogorov timescale for homogeneous isotropic turbulence, where again the dissipation rate is estimated from the turbulent kinetic energy and the integral length scale. And that is again shown here for the example of this premixed flame, isothermal without any combustion or with combustion. You see here this temporal autocovariance, yeah? Because of the normalization, it starts at 1, and over time it decays. And then by integration again, maybe take this example here, you would take the first zero crossing, take this integral, and you have the integral timescale, which is in the order of milliseconds. And then calculating the Kolmogorov timescales, the shortest timescales you will have in your flow field, those are in the order of many, many microseconds. Compare that to the nanoseconds you have in the laser. So by that you can really make instantaneous measurements without any temporal filtering. And so that's why the resolution in time is much better, such that the comparison of power spectra, for example, would be better done in the time domain than in the space domain. So we come to that when we discuss large laser Doppler velocimetry in some more detail, how you use then these correlations to come up over Fourier transform with power spectral densities. So my advice is, if you're interested in these calculations or in these parameters, you should do it in the time and frequency domain and not in the spatial and wave number domain. Okay.
We had in the lab a couple of discussions about this because theoretically the frequency response should be limited by the inertia of the C particles.
But that's true anyhow.
Yeah, so but the thing is that so looking at some of these computed quantities, I never really saw the filtering effect.
I will show it.
Yeah,
it comes to that when we switch to the next chapter. Can we maybe wait to discuss that when we have seen that? Okay, to finalize that, of course, you can do point-wise measurements. 0.0d means limited by these extensions I've discussed. You can use it along a line. Here we have as well restrictions. Let's say, let's make a quick drawing. This is your lens. You have here your expanded beam. You have then first, according to the geometrical optics, something like that. And then you have, in reality, something, a focus like that. And then you have here a certain length where you have more or less parallel waves going through your probe volume. And then, depending on the focal length, this elongation depends on your focal length. And if you want to do a 1D measurement with high resolution and using a focused beam like that, maybe you're restricted to a couple of millimeters only. If you want to have then a larger extended 1D probe volume, you have to use telescopes that you have here a parallel beam intersecting your device. And then it's difficult to make it 50 microns. That's very difficult. And so it's really a trade-off. It depends on what you're after. I cannot give you a general solution to that. Sometimes a single lens is better, and you have here only maybe a couple of millimeters where you have more or less a constant diameter. In other cases, it might be better to work with a telescope and then have less resolution perpendicular to the beam propagation. All right. That's about a few more thoughts about these restrictions in optical diagnostics. Unless you have any questions. Yeah? Yes, please.
In order to estimate whether we are enough resolve in a space and time, we compare our results regarding the Kolmogorov frequency and Kolmogorov scale, right?
Yes.
But in non-reacting, there is no problem. But if you have a reacting flow, estimation of the kinematic viscosity depends on temperature, and since the
Exactly.
heat rules change the density.
Yes.
So how do you want to compute that?
It's a good question. So typically, because the viscosity goes up, for example, in terms of mixing, the restrictions in terms of the resolution are getting less important. So it's not a non-reactive flow in that sense is more critical, because the viscosity is in the nominator. And thereby it's getting better. But you have other restrictions, for example, scales in the flame front of a premixed flame. That is not given here anyhow. And so if you're here, let's say in atmospheric conditions for a premixed flame, you would have a flame front saying, let's say, from 10 to 90% increase of the temperature within, let's say, half a millimeter. Then you want to discretize that, let's say, with 10 samples. That means you need a resolution of 100 microns, perpendicular to the flame front. Doable, but at the limit. If you go to high pressure, and maybe everything shrinks down to 100 microns, you're lost. You can't resolve it.
I've read a couple papers that claim that the smallest flame structure is going to be an order of magnitude maybe 10 times the Kolmogorov length. That eddies on the size of the Kolmogorov length scale are not strong enough to perturb a flame structure. So, do you think for a measurement like PLIF, do you want to resolve all the way down to Kolmogorov, or is there, or can you fully resolve it at a smaller resolution?
Go for high resolution only if you're forced to.
Okay.
Yeah, and so it depends on the question. So I doubt that you easily can resolve the flame structure with OH PLIF, for example. The reason, you have an intensifier. And that is maybe then the limiting part, where you have at best, the best image intensifiers I know of are in the order of 60 line pers per millimeter. And then we're talking about a resolution with this Rayleigh criterion. This is 10-15% modulation depth, so not very well resolved. And so if you have this order of magnitude, then still for high Reynolds numbers, you will not be able to resolve these scales. And then the question is, with an intensifier, I think you're lost anyhow. So to resolve these structures, you would need a technique that doesn't need an intensifier, but just a CCD camera. And then it's not much left than Raman or Rayleigh. And then you need a long time and good budget to be successful for that. So worldwide, only a few labs are doing that, and it's painful. I know that. Okay. Yes, please.
Your definition of spatial resolution and spot size seem to be based around kind of like a point measurement.
Yes.
How does that correspond to like a sheet?
Well, when you have a sheet, it is not only the in-plane resolution that would be important, but as well the out-of-plane. For the out-of-plane, the same restrictions or arguments would hold that I discussed over here. For the in-plane resolution, it depends now on your imaging system. And that depends, again, on your working distance. It depends on your lens. And depends, of course, as well on your discretization at the camera side. So many aspects coming together. And you could say that there, with a typical working distance, you have restrictions in the same order of magnitude. Let's say 20 microns are maybe resolvable in the visible. Yeah? Without an intensifier. If you have an intensifier, it's worse. Yes? Answered?
Yes.
Okay. So then let's take the remaining half hour or so to have a closer look into the first technique to be discussed, particle-based velocimetry. I would like to start with a side note. Of course, there are ways as well to avoid particles. So for certain applications where particles are prohibitive, you can as well use purely spectroscopic methods. Avoid me-scattering, where particle-based velocimetry is built on. Here, you know from textbooks about the Doppler shift. For example, if you do absorption spectroscopy, your static sample would show an absorption line spectrally at a different position than a sample that is moving along a certain direction with a main speed, a main convection speed. And so this is visualized over here. For example, in absorption, you have here a laser, and then it's about the projected velocity onto this laser direction, which is v times cosine of this angle theta, giving rise to a Doppler shift, which is visualized over here, where your absorption profile, maybe that has something like 0.2 wave numbers in full width half maximum, is shifted such that you can distinguish the shift of the central frequency. And by my own experience, you need not only time to resolve that line profile precisely, so you do that typically in a line scan, but as well you need a certain velocity magnitude, minimal velocity magnitude, such that you can distinguish these peaks. And that for gaseous flows, let's say using NO as a marker, is in the order of 30 meters per second. So if you go for combustion devices where you have a clear direction of flow and you're interested in that, and you're heading towards supersonic combustion, that might be a good choice. Yeah, it's doable. And some people have done that in the 90s, and I'm not sure whether still, I don't know any group doing that anymore for the moment, but in principle it's doable. But it's not discussed here because particle-based methods are so much more popular that they're much more important. And we distinguish here laser Doppler velocimetry and particle image velocimetry. As the name says, LDV, based on heterodyne technique, is using the Doppler shift, and I'm showing here only a very simplified argumentation to explain how this technique works. And in PIV, a very completely different techniques. We have seen that already where you take images of me-scattered particles and then try to correlate them to come up with velocities in a field. And laser Doppler velocimetry that is restricted to something like points, extended points, meaning something like 0.5 millimeter in length, maybe at best 50 micrometers in diameter. So for those of you who have not come across me-scattering, that's a phenomenon that is well known, that is scattering of electromagnetic waves of spherical particles. Maybe this is a bit misleading. Here, these aerosols might have larger diameters than the wavelengths. So actually, this is maybe more geometrical optic scattering, which is easier than me-scattering. Me-scattering occurs if the droplet or particle size is at the same size, the same magnitude as your wavelength. Okay? If you have, again, 532 nanometers, for example, then this would be 0.5 micron-sized particles that would give rise to me-scattering. If they are larger, then we call that the regime of geometrical optics. And maybe that is more that regime, because here the fog might have, I don't know, particle sizes more in the order of many microns, 10, 20, 30 microns, and not 0.5 micron. However, here you see visualized what actually happens if a ray of a laser comes to a spherical particle defined by its different index of refraction. You have here at this phase transition from gas, typically maybe to liquid, like an oil, a reflection. Part of it will penetrate into that droplet, and then you have here a first order refraction. Another part, not shown, would as well be internally reflected, and you would have here then second order refraction coming out here, giving rise to rainbow, and higher orders, of course, continuing. And then you can, for spherical droplets, analytically solve the scattering process, and this is shown here for a micrometer-sized glass beads. You see here 0 order as a solid line, dependent on the scattering angle. 0 means forward scattering, so in this direction. 180 means backwards in this direction to the left. And first order, which is this dashed line over here. And depending on the scattering angle, that is more important for phase Doppler anemometry to know that, is that you have contributions that might differ depending on the angle. In some cases, first order is much stronger than 0 order, and in others, it is vice versa. So you have to know at least a little about it. In laser Doppler velocimetry, for example, if you have a signal problem, it is better to look in forward direction than in backward direction. That needs, of course, then additional optical access. But in signal to noise, it makes a difference. Okay, so the idea is that you not measure directly the gas velocity, but you seed particles into your gaseous flow, and what you measure is actually you track the particle velocities, and you have to make sure that the particles are following as good as possible your gas flow. Yeah, you're measuring particle velocities, and that is, of course, as we have discussed already briefly, that is a filtering characteristics. So you want to reduce the so-called slip as far as possible. So the slip is simply the normalized velocity difference between the fluid and the particle. And let's say you would accept a slip only of less than 1%. So you need to find particles that fulfill this requirement. And then you can refer to this cutoff frequency. It's not derived here, but that's the result. Based on the slip, let's say 0.01, you put in here, based on the particle response time, which depends on the particle density of the material, the diameter that is going in over the surface squared, and the dynamic viscosity of your fluid, you see that you have a certain cutoff frequency that is then the result. Moreover, in combustion, you need as well to have chemically inert particles in case you want to measure the velocities as well behind the flame front. And that means as well you need to have materials that have a melting point which is higher than the adiabatic flame temperatures. And those are in the order of 2000, 2500 Kelvin, and that restricts you very fastly to certain materials, because in that cases oil droplets are not cannot be used in post-flame regions. Or if you go for gas turbine combustion where you have preheat temperatures already of 600 K, forget it. Oil will not work. And oil is so much better than anything else for seating that this is really a pain. And of course, different people are using different materials. Here are 3 choices. Magnesium oxide, all of them are ceramic materials with high melting points between 1800 and 2800 Kelvin. But the problem is they have high densities. That is, per kilograms per cubic meter, meaning 3 to 4 tons. Yeah? Compare that to air at 20 degrees Celsius, it is more than 3 orders of magnitude difference. And so you actually do have a problem that these particles do not follow the flow if you have a turbulent flow with high fluctuation levels. And here, referring back to that equation, you can now calculate this cutoff frequency. And this cutoff frequency in a logarithmic scale between 100 hertz and 100,000, a million hertz, you see that over temperature, where the viscosity changes, for magnesium oxide, looking back, that is this material with 3.5 tons per cubic meter. And you see around 400 Kelvin, if you have 2 micrometer sized particles, you have a huge cutoff, a very small cutoff frequency. You cannot resolve more than 800 hertz. That's nothing. Yeah, it's not very good. If you go to smaller particles, okay, it's getting better. It's maybe around 10 kilohertz. But compare that to hot wire anemometry, which is just a second, which goes up another order of magnitude. You have a low pass filter characteristics, and that has to be kept in mind. And so, however, even if you would have a higher frequency resolution, you would need as well a higher spatial resolution. And there's no sense making a high time resolution without having a high spatial resolution, because then you don't look for the smallest eddy, but you have something averaged. And so that goes hand in hand. And so it is not too bad if you restrict yourself to small particles. Going smaller, you will lose signal. Yeah, that as well nonlinear depends on the particle size, and you might not, you cannot afford, let's say, 5 nanometer scaled particles. You wouldn't see them. The good message is, if you go into the flame, because of the higher viscosity, the restrictions are not as bad, and you can resolve with the small particles as well. Frequencies clearly above 100,000, which is far beyond what we can do spatially. Okay, your question.
I was just curious, for the seating materials, what properties other than a low density and high melting point would you want your seating materials to have?
You want to have them that they do not stick to each other, okay, because typically that is a problem. You have, unless you have dried air. So in my lab, I have the infrastructure to have, we dry the air for a dew point at 2C, that helps. But it's if the seeding material is in your tank and you cannot prevent any humidity, that's as well a very, very important quantity. Yeah, to say another one. But your question was about the frequency, the cutoff. Who was asking the? Oh, it was you. Is that answered with that?
Well, so the thing is that in the practical evaluation of the spectra, I did not really see the effect of this cutoff. It was not very evident. So I was wondering if you have any experience how strong it actually is.
We have looked at that in a jet flow, a turbulent jet flow, and actually for that cases we used maybe something like a micrometer-sized particles. It was not as evident as well, but theoretically it is clear, I think, that you cannot expect some, depending on the conditions, more than this limit. Yeah, and as I said, it is as well dependent on your spatial resolution. And as long as you do not have that high spatial resolution to resolve the smallest eddies, and that is difficult in LDV, because at least in one direction you have much more than 50 microns, more on the order of half a millimeter, you're spatially smoothing, and thereby you might not be able to see that effect anyhow.
So, no, that was the interesting case, because I know that the spatial resolution was, for at least one of the cases, the spatial resolution was better than the corresponding temporal resolution.
Okay.
So I would have expected the spectrum to start clearly
Yes.
falling off at
Okay.
the frequency response limit. But
Yeah, we couldn't
it
see it.
was not very evident.
Okay. So there I have no direct answer to that. I would have expected if you have the spatial resolution, then you would start to see it. Yes?
I just had a comment about the mean scattering signal decreasing, because you're right about the nanoparticles, but I was surprised to find that if you calculate the cross-section at 90 degrees,
Mm.
POV or something, but over that size range, 500 nanometers to 2 microns, it actually doesn't change much, the average scattering cross-section. So you can easily afford to use those sort of particles in that case.
Okay.
Yeah, that's what I found.
Okay. Interesting. Maybe we discuss that later. Okay.
So that's a good question so if you actually look before and after combustion, don't you see actually then a step in your particle size? Because what you actually shoot into the combustion chamber forms is a form of initiation for deposit growth.
Oh, that's typically not a problem. Deposit growth is actually, when you look at these particles, you can't resolve them anyhow. Even if there would be something, you wouldn't see it. You have no chance to see that. Then you're talking about something which is in the order of, let's say, films in the order of nanometers. No chance to see that with those resolution. It might happen, but depending on the situation, but not here. Not visualizable. Okay. So how to seed that? And this is black art. Different groups came up with different ideas how to bring in this seed material. Some people have using something like a tank, and then you have here the flow to be seeded, better shown over here. And then there's something like a mesh and a rotating brush. That's one possibility. Actually, not so good experiences. To my understanding, or to my experience, the best is actually something like a fluidized bed, where you have here your tank with your containment, where you have your particles in, and then you send here, let's say, your gaseous flow. You create a fluidized bed. You have here a contraction with a small aperture, a small nozzle that accelerates the flow, and thereby, even if you have, by humidity, particles that stick together, by the forces during this acceleration, they partly break out and disconnect again. And very important is that you do have here a bypass. A bypass because you want to control the seeding density depending on your needs. We'll see later in PIV, LDV that might be different. And as well, in situations like the gas turbine combustor, if you operate that seeding your windows will be covered within a couple of seconds, and you prepare for measurements, you heat up and so on, and you will send all your mass flow through the bypass. And then only the few seconds before you take the measurements, you control that here and open that and wait that the system has been stabilized, and then do the measurements. And so this actually seems to me an appropriate choice how to seed that into the flow. But of course, experiences might be different, and there are as well other concepts. Okay, a few words now about laser Doppler velocimetry. That's maybe what we can do today. I refer myself here only to a very simplified, let's say, visualization of the process. It is not the real physics about the Doppler and the Doppler effect and the heterodyne technique. We do it in this pictorial view. So assume you have two laser beams, and these are continuous wave lasers, not pulsed. Continuous wave lasers with a good beam profile. Let's say you have here something like a Gaussian distribution. Although I show only plane waves, it would be something like that. And they have the same polarization, and they intersect. And they intersect with the crossing angle that you define. Then you can calculate the difference between these stripes of interference. Yeah? These interference stripes have a certain displacement, and this displacement depends on the crossing angle phi of 2 phi and the laser wavelength, which is as well known precisely. And then assume you have now this probe volume, which might extend in this direction, as I said, maybe half a millimeter, a millimeter, depending on the crossing angle, can be as well 2 millimeters. And depending on the lenses you're using, maybe this diameter is in the order of 50, 100, maybe 150 microns. And then the particles which are seeded to the flow are going through this interference pattern. And then you have me scattering, no me scattering, me scattering, no me scattering, giving rise to a so-called Doppler burst. This is the Doppler burst. And now, what you do in post-processing, and that is done online more or less, you estimate the time of flight between these interference patterns. Yeah? And you assume in all of these commercialized LDV systems that you do not have any acceleration during the transit. You get an estimate of the mean transit time from one to the next interference stripe. And that means you can trace back, with the knowledge of the spacing between these stripes, you trace then with the particle flight time directly back to the definition of the velocity, which is perpendicularly oriented to this pattern. So you measure in this experiment, in this visualization, only one velocity component that is typically linked to one color. Yeah? Let's say here you use an argon ion laser, for example, use 514.5 nanometers. Then your me scattering is as well the same wavelength, and you know this velocity component at this color is along a certain direction. And that is now what we call an instantaneous velocity. Yeah? But it's not instantaneous. It is averaged with a particle flight time through this pattern. There's one problem with that. If you would do it, you have a direct correlation between the frequency, that is 1 over the transit time, versus velocity. And if a particle would come from top or bottom, you would not be able to distinguish that. You would have here a negative velocity for particle B. Let's say this is negative direction. And here for particle A, you have a positive velocity, the same magnitude, but as well different signs, but the same frequency. So the trick in LDV is to shift this line slightly. And how do you do that? You're not working with a lab-fixed interference pattern, but you make your interference pattern moving. And this is done by having not identical frequencies or wavelengths that are interfering, but one is slightly different from the other. And this will be shown in a second. And if you have that, then particle A coming from top sees a higher frequency. Yeah, it's now a higher frequency than there. And a particle coming from the bottom, particle B, running behind the interference pattern with this velocity, shift velocity, sees or creates a smaller frequency. Particles that are at rest, they would see here directly the so-called shift frequency. That is the frequency with the speed the interference pattern moves. Whereas in the upper case, where you have a stationary interference pattern, a particle that does not move would not give any frequency. It would be frequency 0. Okay. And this is visualized over here. I hope that works better. On the left-hand side, we have the case without any shift. You see here the waves, exactly the same wavelengths. They interfere. You see as well nicely by the superposition that the electromagnetic waves would move from right to the left. But I have to warn you, this is a wavelength that we can see by eye. Of course, if you now use a laser in the visible, this would be in the order of 500 nanometers, for example, green light. Yeah, this is hugely magnified. And then, however, you see as well these stripes. That would be a constructive interference. Yep. But you see as well these gray areas over. This is destructive interference. And then the particle A and B from top and bottom, that would give rise here to Doppler bursts. They are now made symmetric with the same frequency. And this is now different. If you go to this pattern, where now the waves come from the left, by eye, it looks like the same frequency, but it's not. Try to follow these stripes here. I try to follow with the pointer. And start again here. They move upwards. And that means, although both particles have the same magnitude, but different directions, the Doppler bursts are different. That's the simple idea. Got it? Of course, the question is how to do it. And that is done in a so-called BRexit cell. I do not go into detail. What you do is you take a cell where you have a piezo transducer, maybe operated typically at 40 megahertz, and that creates acoustic waves that travel through the crystal from one to the other side. At the other side, they're damped. And then physically, that is called a so-called phonon. And a photon and a phonon, they can interact, and there is an energy transfer. And this energy transfer, depending on the acoustic frequency, is changing the light frequency. And so 40 megahertz, for example, if you have a light wave, a light frequency in the visible 10 to the 15, 40 megahertz is almost nothing. You can't see that. And spectrometer wouldn't see that as well. But you can nicely visualize that in this heterodyne technique. Okay? And so the simple setup is shown here. You have here a CW laser. In former times, it was an argon ion laser with different frequencies coming out. Nowadays as well, you have solid-state lasers. You split it into two beams. At least one beam must be frequency modulated by this BRexit cell to have these moving interference stripes, and then you can have here your probe volume. And to have more than one component, you use now different colors. These are shown here in yellow and red. Maybe it would better in argon ion lasers, it would be green and blue, where you then have, I do it with my hands, interference pattern in this direction for this velocity component, and an interference pattern in this direction for this velocity component. And then you would need a third one, which is aligned perpendicular to the other both, and that needs then another transmitter, because then you need an interference pattern in this direction. And that cannot be handled by the same lens. So 3 velocity components in LDV is therefore a big effort. It is expensive, and therefore it has not been done and realized so often. And you have this cigar-like interference pattern. Maybe I should draw that again. The interference pattern is elongated in this direction, and only in the perpendicular direction it is much shorter. So you have something like a cigar-like probe volume with the stripes over here. And if you now overlay another cigar for the third component, then you have not exactly matching probe volumes as well. That can be a problem. Okay. Commercialized systems, you find it from Dantec, TSI, that are, I think, the most common providers, but there are as well others. Maybe in total less than 5 companies I know of. With the laser, this BRexit cell, the different outlets for the different colors in case you have an argon ion laser over here, and then the receiving optics. Sometimes you use in backscatter the same, the sending and receiving optics are the same. Very often as well, if you look for higher scattering intensities, you might use as well a different scattering angle. Here, this device is actually shown for phase Doppler measurements, where you as well measure the diameter of the droplets, for example. I would like to maybe discuss that as a last point. You have to be aware of the fact that in LDV, you typically measure over a certain time. Let's say you give yourself a minute for each probe volume. And you typically don't go for, let's say, 1 hour or so, because you have to do it point-wise. And that takes a lot of time. And let's say you go for a minute. And then let's say you measure then at a single point with this time restriction, maybe 2 components, to come up then with statistically uncorrelated data. So there's one thing you have to be aware of. Let's say you have a bifurcation in your flow. Sometimes your probe volume is in a region where you have in average 1 meter per second, and the next moment it's 10 meter per second. Okay? And this flapping would be the same probability. Then, if you would not do this transit time weighting shown over here, you would end up with a mean velocity which is biased. Assuming that you have the same seeding density in all cases, then you would have the higher velocity would be overweighted compared to the smaller velocity. That is why you do a so-called transient time weighting, where you multiply the instantaneous velocity with the transit time. And the transit time is the time you need, or a particle needs, to cross your interference pattern, yeah, to travel through this distance. And if you have a small a slow particle, this takes longer, and the weighting factor is higher compared to a fast particle, which is, of course, then as well, assuming same seeding density, appearing much more often. And thereby, by this trick of weighting, the fact that you have slow and fast particles is weighted out. And that's why as well now you do the normalization here not by the number of samples as you learned in statistics, but you do that by the integration of the transit time. And this idea goes through all the other quantities, not only for the mean velocity, but as well for the velocity variance, where you have now the fluctuation values based on the Reynolds decomposition. You can take the root mean square of that. That is then called standard deviation. We have discussed before the turbulent kinetic energy that is calculated based on the standard deviations here, assuming an axisymmetric flow, where you have here, that's why twice the radial component, but in a normal turbulent flow where you have no axisymmetry, you really have to sum up all 3 standard deviations of all 3 velocity components. You have here the shear stresses, where you have the correlation between, let's say, axial and radial velocity component, for example, very important for turbulence modeling. And you can as well, a bit more detailed now, calculate based on time series covariances. First here shown for the temporal covariance, where you measure at one single location, for example, the axial velocity component at different times and different, as well here it's shown at this is the global definition, where you shift in space and time. But if you do this only in time, then you just do this measurement at the same location, but at different subsequent times, and get the integral time scale that we discussed. What we had not discussed is if you use that by Fourier transform, you then receive the power spectral density. That is the turbulence spectrum of your flow. And that is shown here for an isothermal jet, where the measurement has been taking place at the symmetry line 40 diameters downstream of the exit of the nozzle. And you see here the typical decay that you would expect, how this covariance decays over time, where the integral would be then the integral time scale. And if you take a Fourier transform of this slope or this curve, you end up then with the power spectral density. And it should be, for isotropic homogeneous turbulence at center line, it should behave corresponding to the -5/3 law, which is not the case. maybe it was slightly misaligned. It's not so easy if you have a nozzle, let's say, of 20 millimeters, and you go 40D downstream, you have to find that exactly where that is. And any disturbance from the lab might make this small deviation. However, that looks quite good, and this is based on millions of data points to get this smooth decay of the energy content of eddies at certain size. And that should be interpreted. Large eddies are to the left, small eddies are to the right, and the power spectral density means how much of the turbulent kinetic energy is in a certain spectral range corresponding as well to a certain size of an eddy. And if you're going to smaller and smaller eddies with higher and higher frequencies, at some stage they would dissipate into heat. And that is then somewhere the Kolmogorov cutoff, which we couldn't resolve with this technique. You can do it as well now in the spatial domain. So I mentioned that briefly. Now you have a sketch. You typically have one fixed probe volume, and then you shift the other probe volume. You have a second LDV system, and then you look for the spatial covariance, where you measure this typically at the same time. Delta t is 0, but delta x is now the displacement between these 2 points. And as discussed, you can from that deduce the integral length scale. As well, in principle, you can Fourier transform this expression as well and get now the power spectral density in the wave number regime. But for that, you need really a good spatial resolution and a good discretization. And that means, maybe I should make a drawing out of that. If you now have here the displacement, then for homogeneous isotropic turbulence, you would have a behavior textbook like that. And capturing this initial parabolic shape is extremely difficult. You need a very, very high resolution. And that is why it is easier to make in the frequency domain than in the wave number domain. However, of course, you can do more. You can do it now in space and in time. And that is shown here. Now we have a displacement delta z in this direction and delta t in this direction. If delta z is 0, this would be the temporal autocorrelation. But now this is done here again for this jet, and only 3 curves out of, I don't know, hundreds are shown. What is nice to see, if you now have your second probe volume displaced axially downstream, the correlation is temporally delayed. That's clear. Yeah, because your eddies, they need a certain transit time. A correlation is then measured if you're measuring within one eddy. And this eddy travels from here to here, and this takes a certain time. And this is dependent on the mean axial velocity. And actually, if you now draw a line through this maxima over here, you can prove the validity of Taylor's hypothesis, yeah? Which allows you for this kind of flows to transform between space and time. That, of course, provides a lot of insight into your flow. Here it's known for a jet flow, a turbulent jet flow, but of course for swirling flows, it would be very interesting to do this analysis as well. Very often it is not done. Okay, with that, I'm afraid that my time is over for this morning. So tomorrow we will start up with the particle image velocimetry. I'm grateful for your patience, and if you have any questions, maybe we can take another 2 questions and the other questions after the lecture. So do you have immediate questions, or you are hungry and heading for lunch? Okay, go for lunch. Thank you very much.